terabyte of data going into it. If this is my personal computer and I'm running a terabyte of data into this, this is running rather quickly through all 500 iterations. But yeah, at a terabyte of data, we're talking something closer to days, week, even with a 3.5 gigahertz machine in 8 cores, it's still going to take a long time to go through a full terabyte of data. And then we want to start looking at putting it into some other framework like Spark or something that will be able to process on there more across multiple processors and multiple computers. And if we scroll all the way down to the bottom, you're going to see here's our square mean error of 0.0088. If we scroll way up, you'll see it kind of oscillates between 0.0888 and 0.0089. It's right around 250 where you start seeing that oscillation where it's really not going anywhere. So we really didn't need to go through a full 500 epochs. If you're retraining the stuff over and over again, it's kind of good to note where that error zone is so you don't have to do all the extra processing. Of course, if you're going to build a model, we want to go ahead and run a prediction on it. So let's go ahead and make our prediction. And remember, we have our training test set and our test set, we have the train X and the train Y for training it, or train predict. And then we have our test X and our test Y going in there. So we can test to see how good it did. And when we come in here, we have, you'll see right here, we go ahead and do our train predict equals model predict train X and test predict model predict test X. Why would we want to run the prediction on train X? Well, it's not 100% on its prediction. We know it has a certain amount of error, and we want to compare the error we have on what we programmed it with the error we get when we run it on new data that's the model's never seen before. And one of the things we can do, we go ahead and invert the predictions. This helps us level it off a little bit more. Get rid of some of our bias. We have train predict equals an NP exponential M1, the train predict. And then train Y equals the exponential M1 for train Y. And then we do again that with test predict and test Y. Again, reformatting the data so that it all matches. And then we want to go ahead and calculate the root mean square error. So we have our train score, which is your math square root times the mean square root error, train Y and train predict. And again, we're just, this is just feeding the data through so we can compare it. And the same thing with the test. And let's take a look at that, because really the code makes sense. If you're going through it line by line, you can see what we're doing. But the answer really helps to zoom in. So we have a train score, which is 2.40 of our root mean square error. And we have a test score of 3.16 of the root mean square error. If these were reversed, if our test score is better than our training score, then we've overtrained. Something's really wrong. At that point, you got to go back and figure out what you did wrong. Because you should never have a better result on your test data than you do on your training data. And that's why we put them both through. That's why we look at the error for both the training and the testing. When you're going out and quoting your, publishing this, and you're saying, hey, how good is my model? It's the test score that you're showing people. This is what it did on my test data that the model had never seen before. This is how good my model is. And a lot of times you actually want to put together like a little formal code where we actually want to print that out. And if we print that out, you can see down here, test prediction and standard deviation of data set 3.16 is less than 4.40. I have to go back, and we're up here. If you remember, we did the square means error. This is standard deviation. That's why these numbers are different. It's saying the same thing that we just talked about. 3.16 is less than 4.40. Model is good enough. We're saying, hey, this model is valid. We have a valid model here. So we can go ahead and go with that. And along with putting a formal print out of there, we want to go ahead and plot what's going on. And this, we just want a pretty graph here so that people can see what's going on. When I walk into a meeting and I'm dealing with a number of people, they really don't want these numbers. They don't want to say, hey, standard deviation, unless you know what statistics are. You might be dealing with a number of different departments. Head of sales might not work with standard deviation or have any idea what that really means number-wise. And so at this point, we really want to put it in a graph so we have something to display. And with displaying, you got to remember that we're looking at the data today going into it and what's going to happen tomorrow. So let's take a quick look at this. We're going to go ahead and shift the train predictions for plotting. We have our train predict plot, NP empty like data set, train predict plot, set it up with null values. You know, it's just kind of a weird thing where we're creating the data groups as we like them, and then putting the data in there is what's going on here. So we have our train predict plot, which is going to be our look back, our length, plus look back. Is going to equal train predict. So we're creating this. Basically, we're taking this and we're dumping the train predict into it. So now we have our nice train predict plot. And then we have the shift test predictions for the plotting. We're going to continue more of that. Oops, looks like I put it in here double. No, it's just, yeah, they put it in here double. Didn't mean to do that. We really only need to do it once. Oh, here we go. This is where the problem was, is because this is the test predict. So we have our training prediction. We're doing the shift on here. And then the test predict, we're going to look at that. Same thing, we're just creating those two data sets. Test predict plot, length prediction set up on there. And then we're going to go through the plotting, the original data set, and the predictions. So we have a time axis. Always nice to have your time set on there. Set that to the time array, time axis lap. All this is setting up the time variable for the bottom. And then we have a lot of stuff going on here as far as setting up our figure. Let's go ahead and run that, and then we'll break it down. We have on here our main plot. We have two different plots going on here. The ISPU going up and the data, and the ISPU here with all these different settings on it. And so when we look at this, we have our AX1, that's the main plot. I mean our AX, that's the main plot, and we have our AX1, which is the secondary plot over here. So we're doing a figure PLT, or PLT.figure, and we're going to dump those two graphs on there. And so we take, and if you go through the code piece by piece, which we're not going to do, we're going to do the data set here, exponential, reverse exponential, so that it looks correctly. We're going to label it the original data set. We're going to plot the train predict plot. That's what we just created. We're going to make that orange, and we'll label it train prediction. Test predict plot, we're going to make that red and label it test prediction, and so forth. Set our ticks up. This actually just put ticks, time axes gets its ticks. The little marks there going along the axes, that kind of thing. And let's take a look and see what these graphs look like. And these are just kind of fun. You know, when you show up into a meeting and this is the final output and you say, hey, this is what we're looking at. Here's our original data in blue. Here's our training prediction. You can see that it trains pretty close to what the data is up there. I would also probably put a like a little timestamp and do just right before and right after, where we go from train to test prediction. And you can see with the test prediction, the data comes in red, and then you can also see what the original data set looked like behind it and how it differs. And then we can just isolate that here on the right. That's all this is just the test prediction on the right. And it's, you know, you'll see with the original data set, there's a lot of peaks we're missing and a lot of lows we're missing. But as far as the actual test prediction, it does pretty good. It's pretty right on. You can get a good idea of what to expect for your ISPU. And so from this, we would probably publish it and say, hey, this is what you expect, and this is our this is a range of error. That's the kind of thing I'd put out on a daily basis. Maybe we predict the cells are going to be this, or maybe weekly. So you kind of get a nice, you kind of flatten the data coming out, and you say, hey, this is what we're looking at. The big takeaway from this is that we're working with, let me go back up here. Whoops, oh, too far. There we go. Is this model here. This is what this is all about. We worked through all of those pieces, all the tensor flows, and that is to build this sequential model. And we're only putting in the 2 layers. This can get pretty complicated. If you get too complicated, it never verges into a usable model. So if you have like 30 different layers in here, there's a good chance you might crash it, kind of thing. So don't go too haywire on that. And that you kind of learn as you go. Again, it's domain knowledge, and also starting to understand all these different layers and what they mean. The data analytics behind those layers is something that your data analysis professional would come in and say, this is what we want to try. But I tell you, as a data scientist, a lot of these basic setups are common. And I don't know how many times working with somebody and they're like, oh my gosh, if I only did a tangent H instead of a ReLU activation, I worked for 2 weeks to figure that out. Well, as a data science, I can run it through the model in 5 minutes instead of spending 2 weeks doing the math behind it. So that's one of the advantages of data scientists, is we do it from programming side, and a data analytics is going to look for it. How does it work in math? And this is really the core right here of TensorFlow and Keras, is being able to build your data model quickly and efficiently. And of course, with any data science, putting out a pretty graph so that your shareholders, again, we want to take and reduce the information down to something people can look at and say, oh, that's what's going on. They can see what's going on as far as the dates and the change in the ISPU.
Now, let's talk a little bit about recurrent neural networks. So neural networks are of different types. We have CNN, we have RNN, ANN, so on. Now, RNN is one type of neural network. RNN stands for recurrent neural network. The networks like CNN and ANN are feed-forward network, which means that the information pretty much only goes from left to right or from front to back, whichever way you call it. Whereas in case of recurrent neural network, there will be some information traveling backwards as well. So that is why it is known as a recurrent neural network. And each of these types have a specific application. So for example, convolutional neural networks or CNN are very good for doing image processing and object detection using for video and images. Whereas recurrent neural networks are pretty good for doing NLP or speech recognition and so on. Okay. So for the next few minutes, we will kind of focus on recurrent neural networks, and we will see an example of how we can use RNN to do a time series analysis. So in a typical neural network, this is how it looks, right? So where you have a neuron and then the inputs are coming to the neuron, and then you have an output which goes to other neurons in the other layers. In case of recurrent neural network, what happens is you have the inputs, let's say at a given point in time, but then a part of the previous output also gets fed in along with the inputs for the given time. Now, this can be a little confusing. So let's see if we can take a little expanded view of this. So this is another view of one single neuron, which is what is known as in an unfolded manner. Okay. So if we are getting inputs or data over a period of time, then this is how the neuron will look. Remember, these are not three neurons. This is one neuron, and it is what is known as, it is shown in a unfolded way. Okay. We have unfolded this single neuron over a period of time. So at a given time, let's say t minus 1, an input of xt minus 1 is fed to the neuron, and it gets an output of yt minus 1. Then the next instant, which is xt at a time t, right? There is an input of xt, and then there is an output of yt. So this is a single neuron, but is displayed in an unfolded way. So this is like expanding it over a period of time. So let's start with this part here. This particular neuron gets an input at an instant t minus 1. Let's say time is equal to t minus 1. It gets an input of xt minus 1, and it gives an output of yt minus 1. Then when we go to the instant t, here it gets an input of xt, and it also additionally gets an input from this previous time frame t minus 1. So this yt minus 1 gets fed here, and that results in yt. t. Alright. Then when we go to the time t plus 1, there is an input of xt minus 1 at that given time, plus the input from the previous time frame, which is a time frame of t. That also gets fed in here, and then we get an output of yt plus 1. Okay. So let me explain once again. This is a single neuron. So these are not three different neurons. A single neuron seen over a period of time from t minus 1 to t plus 1. And unlike a regular feed forward neuron which only gets x, in this case the input is x and also another input which is coming from the previous time frame, and that is what this loop is. In this, on the left hand side diagram, this loop is indicating that. Okay, so on the right hand side it is represented in an unfolded way. Okay, so the input, if we take a time frame t for example, is not only xt, which is the input, which is the normal input at the time frame t, but it is also getting an input from the previous time frame, which is this yt minus 1 is also being fed as an input. That is the key differentiator here. Okay. Similarly, at the instant t plus 1, it is getting a normal input of xt plus 1 plus this yt is actually being fed here, and then the output comes as yt plus 1. Okay. So this is the construct of a recurrent neural network. Now, recurrent neural networks again can be of different subtypes. It can be one-to-one, one-to-many, many-to-one, and many-to-many, depending on what kind of application we want to use. One of the examples is like the stock price. So you're feeding, so there is only one input. Only thing is it is spread over a period of time. So you're feeding the stock price input. That is what comes here as an input. And you get an output, which is again the stock price, which is probably predicted over the next 2 days, or 3 days, or 10 days, or whatever. So the number of outputs and inputs is the same. There is only one input. There is only one output. Only thing is it is spread over a time. So variables are not many. Then you have one-to-many. So there is one input, but you're expecting multiple outputs. What is an example of this? Let's say you want to caption an image. So how do you want to do that? What is the input that will go here? It's just an image, which is one input. But what is the output you're looking for? You're looking for a phrase maybe, right? Not just a word, but a phrase. So it's like cat is sitting on a mat, right? So the image is, there is only one image which consists of the cat sitting on a mat, but the output are like maybe 3 or 4 words, which is saying the cat is sitting on a mat. So this is one-to-many, right? Then you can have many-to-one. Examples of this are like you're feeding some text and you want to know the output, whether the text is, what kind of sentiment is expressed by the text. It could be positive, it could be negative. So that's the output you're looking for. So you feed a large number of words, maybe the text may consist of words or lines or whatever. So that is what is the multiple inputs. But the output, all it says is the sentiment is positive. So it is just one output, or the sentiment is negative, just one output, right? So this is many-to-one. Then we have many-to-many. So what is an example of this? Let's say you want to do some translation. So how do you do a translation? You feed in a sentence maybe in a particular language, English, and then you want a sentence actually in another language. So that is like there are multiple inputs. One sentence can consist of multiple words, and the output also is a sentence consisting of multiple words. All right. So how do we implement RNN? This is an example of implementing an RNN for a particular use case. So in our particular example, we have the data about milk production over a few months, and using RNN, we want to predict, because this is time series analysis. So RNN is good to do time series analysis. So using RNN, we want to predict what will be the milk production in the future. So let us see how we can do that. I will first take you quickly through the slides, and then I will actually run this in a Jupyter notebook. The code, I will run it in the Jupyter notebook. So this is how it looks, the code looks. So while this is TensorFlow, you still use the standard Python libraries like NumPy and Pandas and even Matplotlib to do some initial processing, getting the data, processing it, cleaning it, whatever. All that can be still done within the same program. So that's what we are doing here. We are importing some libraries like NumPy and Pandas, and then we read the data file. And if we plot the data, we see here it is the data for the years 1962 to 74. 5, and we can see that there is a certain trend, right? So this is how a typical time series data would look. Again, some of you, if you're not familiar with time series and time series analysis and so on, I would recommend you to go through some videos around that, which will make it easy to understand this. So this is how a typical time series data would look. In this case, it is nothing but there is only one variable, which is milk production, and it is spread across several years. So it's going from 1962 to 75, and that value has been plotted. So if you see, there is a certain kind of a trend here, which is basically going upwards, and there will be some seasonality. So time series data has these three components, right? So it will have a trend, it will have a seasonality, and then it will have some randomness. So that's what this graph is showing. And now if we want to perform analysis on this, time series analysis on this, first thing we need to do is split the data into train and test. And in this case, we will just use a straightforward method, which is taking the data for the first 13 years. So the idea here is we need to train our model, right? This is time series data. So and we want to predict for the future. So the way we need to use this is we have to take the data for a certain period of time and train our model. And then we use a part of the known data so that we can then ask our model to predict for that duration and compare it with the known information. So what do we mean by that? So here, if you see this data, I will show you in the notebook as well, Jupyter notebook as well. This has 13 years of data. So what we are doing is we are taking the first 12 years and using that as our training set, right? So 12 years we are doing, and this has about, I think, 14 years of data. So we are taking 13 years of data for training purpose, and then we are using the last 1 year, remaining 1 year of data for testing purpose. Because here what we can do is this 1 year data, we know the values, right? Because if we want to compare the accuracy or anything like that, we need to know the values. So in this case, we know the values of this one particular year. So we will use that. But at the same time, we train the model for 13 years of data. And for the 14th year, we will ask our model to predict and then compare it with this known value so that we know how accurate our model is. I hope that makes sense. Okay. So that's what we are doing here. 156 is nothing but 12 into 13. On a monthly basis, we get the data. The next step is to scale the data. This is all regular data manipulation, data munching activity. And then you split it. You are basically assigning the train and test data to the scaled variables. And then you need to read the data in batches. So it is very important, as I mentioned earlier also, that instead of reading the entire data in one shot, you feed the data in batches. So in order to do that, we are writing a function for that. That's all we are doing here. So that is still here. What we have done is regular Python programming. There is no TensorFlow as of now here. Okay, so far what we have done is preparation, data munching. Now what we are doing is actually training our model. So this is where TensorFlow now comes into picture. So we are importing, first step is to import the TensorFlow library. So this is how you do it, import TensorFlow as TF. And then you can define some variables or constants, whichever way. Now here, of course, there are a couple of ways of doing it. You can create them as TensorFlow nodes, but that is a little bit of an overhead. We will just use the regular Python variables or constants. So here I am creating regular Python variables and I'm saying number of inputs is 1. So instead of hard coding, I'm just storing them as variables. So this is number of inputs is 1, number of time steps is 12, number of neurons is 100, and so on, right? And then learning rate is 0.03 and number of iterations we are saying is 4000. Then we create placeholders. Now we will be storing the independent variables in X and the dependent variables in Y, and this we will read from an external file. Remember, I told you placeholders are used for getting data from outside and then feeding it to our model. So that's the reason we have two placeholders, one for reading the X values and another for reading the Y values. In this step, we are only just creating the nodes, right? So this is just creating the graph. And similarly, we are mentioning what is the loss function and what is the optimizer and how to run the optimizer. And once that is done, you are initializing the variables and then you're creating a saver variable or a saver instance. So saver is basically nothing but in machine learning, you can train your model and you can save it for later use. So that's where the saving comes into play. We will see how to use that as well. And then the last step is to create your session and run this graph. right? So we are initializing the variables. Remember this, we run init, so which is nothing but this one. So we are initializing the variables, whatever are there, instead of hard coding. Remember in earlier case we were hard coding how many iterations. So here we are saying for the given number of iterations which are stored in this, maybe how many iterations we said is, what is the value of iterations? This is training iterations is 4000. So we specify that based on the number of training iterations, next batch will basically fetch the data and then we run the session. We are basically saying train is the node which we will run in the session, and this will basically train our model, and this is more for printing. Every 100 times you print it, that's all. There's nothing more to it. So for example, the output would look somewhat like this. This is for 0, this for 100, next for 200, and so on. Okay, and then you save the model. You remember saver we created, so you save the model for later use. So this is our test data. Remember we are doing this on training data, right? So once the training is done, we then try to create the inference on the test data so that we can compare how accurate this is. Right, so this is how the test set would look, and then we will basically restore this model, okay, because in the previous slide we created the model and we stored it. So now we have to restore the model and then run our test data against it and see what are the values that are predicted, what are the y values, and then compare with x to see the accuracy. So train seed is what we are seeing here. So that is what will have the predicted values, and these predicted values, what we want to do is we want to create an additional column, because remember we need to compare, because we want to find out the accuracy of this model. So we need to compare the predicted values with the actual value. So what we are doing here is adding another column called generated and assign a value to that. All right, so this is the result of the prediction, and then if we need to reshape, because we have to show this in the form of monthly results, so that's what we are doing here. And once we generate the results and then display it, we can actually see it month wise here, and the actual and the generated values. Okay, so we create a data frame which is a combination of the actual values and the predicted values from the test set. And then we can plot to see how the trend is. As you can see, pretty much the actual value is in blue color and the generated or predicted value, the curve is in yellow color. The trend is maintained. So it will probably, it's not 100% accurate, but the trend is maintained. All right, so let's do one thing. Let's go into the Jupyter notebook and take a look at how this works in TensorFlow environment. Actually, the code, I will walk you through the code. This is my Jupyter notebook, and the data is taken from this particular link. In case you're interested, you can download it from there. And this is the data for the years 1962 to 75. The first thing we do is import these libraries, because before we start with the actual TensorFlow activity, we need to prepare the data and so on. So for that, you can use your regular Python libraries, which are like NumPy, Pandas, and so on. So that's what we are doing here. And then we read the data using Pandas into a data frame. So this is a data frame, milk is a data frame, and we will do some quick exploratory analysis just to see how our data is looking. Initial 5 records that we'll get, 1, 2, 3, 4, 5, that is the head. So it goes from 1962 January to 1962 May. Once we rechange, or basically we need to split this into month specifically separately. So that's what we are doing here, date to time. So we kind of do a little bit of a reindexing, and then if we plot this, this is how the data look. As you can see, there is a clear upward trend, and there is some seasonality and so on, but anyway, we will not break that up into those components. We will just use RNN to predict and test. Okay, so the next thing is to check some, if we can do run like an info, it will tell us what is the information about this data set. So let us just run that. Okay, so it is just telling us how many total columns and what is the size of the file and so on and so forth. Again, in case you're interested in doing some exploratory analysis. So what we'll do next is we will take the 13 years of data for our training data set. So what are we going to do now? Let me step back. So what have we seen here? We have seen that there are 168 records, so which is nothing but 14 years of data. We now have to split this into our training and test data set. So how do we do that? I think in case of time series, we cannot do it like 80-20 like we do in normal splitting in normal machine learning process. Here it is time series data. So what we are going to do is we will take out of this 14 years, we will take the first 13 years of data and we will use that for training, and then we will test it with the last, which is the 14th year data. We will use it for testing. Okay, so that's what we are going to do here. So let's split that. So training set will consist of my 156 records, which is nothing but 13 into 12, right? My 13 years of data I'm taking for training, and then my test set will consist of the bottom 12 observations, which is last 1 year of data, which is the 14th year. Okay, so that's now done. Training and test splitting is done. The next step is to do some normalizing, which is basically we'll use, or scaling rather, we will use min-max scaler, and we will just scale the data. And now we do it for both test as well as train. Now we are ready to create our RNN model. But before that, one quick thing. In order to fetch the data, we have to create a function. So that's what we are doing here. We create a function called next batch, and how you want to fetch the steps, they are all defined as our constants, if you remember, and that's what this function is all about. So we define that function. We will be calling that in our training method. All right, so from here onwards up to there, we are done with the preparation of the data and whatever functions or whatever are required. From here onwards is where the TensorFlow part starts. So the first thing we do is import the TensorFlow library. Typically this is a very standard way of importing the library. We say import TensorFlow as TF. Now TF is nothing but a name, so you can change it to TF1 or ABC or XYZ, whatever. So this part you can change, but by and large everybody uses this, so I would rather recommend you also use the same syntax. So you say import TensorFlow as TF, so it's very easy for others to understand as well. And then you declare or define a bunch of constants. That's what we are doing here. Like for example, the number of time steps, in this case it is 12, number of neurons, there are 100, number of outputs, it is only 1, and so on, right? And then the learning rate and all that, we are declaring or defining those variables in this particular block. Next is to create placeholders. You remember the placeholders are used for feeding the data. So we have X and Y. X is for the input, which is the independent variable, and Y is the output, which is the dependent variable. And in our case, these are not different characteristics or features, but it is the same one feature or one variable, but it is over a period of time. So that's the only difference. So that's what we are doing here. And now we need to create our network, right? The neural network. So in our case, we said we will create a RNN layer. Now there are different ways or different formats of RNN, which is probably not in scope of this module. So for now, we will just assume we are creating one RNN layer, and one type of RNN is GRU cell. So we will use GRU cell, and we use this APIs for creating our layer. So each cell will be with an output projection wrapper. There is a need for doing that. And again, the details of this we will probably do in another video where we talk in detail about RNN. So for now, we are creating a GRU cell with the wrapper, and the syntax for creating the GRU cell is like this. The number of units, which we said there should be 100 neurons. What will be the activation function? In this case, it is ReLU, and then number of outputs. In our case, it is only 1. Okay, so we create the cell here. Okay, then we got the GRU cell, and then we say what is our output, which is nothing but we get the outputs and the states and their states, and which is the way we get that is tf.nnn.dynamic_rnn. So if we call this and we pass the cell and the data, which is basically in placeholder. So again, remember, all we are doing here is we are creating just the nodes for the graph. So nothing is actually getting executed from a TensorFlow perspective. Okay. All right. So once that is done, now we need to pass this calculate the outputs and the states using the dynamic_rnn method, and we pass the cell as a parameter and then the x values as a parameter. And if we run that, we will have the outputs and the states. And this is where we actually run the training method. So, or create, not really run the training method, but we create the nodes for the training and the optimizer. Then we have the initialization of the variables, and we save this model, we create a saver object just to save the model, because we will then restore it and run it to do our predictions. So this is what we will do here. So that is another node, and this is where we actually create a session and run the training. Okay, so let's go ahead and do that. That will take a little while because we said 4000 iterations. So we will allow it to finish. We will probably come back once the training is completed. Alright, so the training is done. Now let's go and run this on the test data. So let's just quickly take a look at the test data set. So this is our 1 year data for the year of 1975. So if we see this is from January, February and so on. And we will pass this to our model. So what are we doing here? We are restoring the model here, for example. Right? This is the path that we have given when we were saving the model. Let's go back once and show you. Let me show you where we did the saving of the model. Yes, so we saved the model here. So that again we will restore that, and we will use that to run it on our test data and see how well it predicts. So let's go ahead and run this, and this is just 12 records, so this will not take time. Remember, I told you training is what takes a lot of time. The regular inference, this is called inference, doesn't take much time, right? So it just depends on how much data. There were only 12 records here, so it was very quick. But in training, what we do, we pass this multiple times. There are iterations, 4000 iterations we did, for example. So that takes longer. And in general, in machine learning, deep learning, training is what takes the maximum amount of time. All right, so let's go ahead and see the results. We will, in order to plot it, we will have to kind of adjust the format of the results. Otherwise, we will not be able to see it in a proper way. And then we will, so this is our, so what we have done is we created a data frame which consists of the predicted value and the actual value. So this is the data frame. So this is the actual value, this 834, 782 and so on. This is what our model has predicted. So it may not be so easy to see in a tabular format. So let's go ahead and plot it so that we can compare these two. So when we plot it, you will see that the trend is more or less maintained, right? So we go from the blue color is the actual values, and the yellow color or the orange color, whatever is it, is the one which is generated by our model. So it pretty much is following the actual trend. So not bad for such a quick iteration and training.
This tutorial is about object detection. We will walk you through a TensorFlow code using which we will do object detection in images. We will tell you what are the libraries that are required, a little bit about the COCO dataset, and then we will show you the implementation code itself, a demo of the code. Alright, so let's get started. So what is the TensorFlow Object Detection API? It is an open source framework which is actually provided by the TensorFlow team, and there are trained models available, and the sample code is also available which we can use in order to easily detect objects in images and videos. This is pretty robust and can detect objects fairly quickly, and this is very easy for people to use as well. People with very less or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. This is a list of libraries that are required, and they have been shown in the code as well. The exact purpose of each of this library, why it is required, is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The COCO dataset, COCO stands for Common Objects in Context. So this data set consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source. And let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial, we are using this SSD model, which is SSD MobileNet version 1. So that's the model that we'll be using. So in this cell, we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. Might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is, your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now each of these will obviously, the numbers will not make any sense to the outside world. So we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I'm storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach 1, beach 2, beach 3 and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2 and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically will be filled with either 1, 2 or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop, and what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected, and then against each of the object a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code. And here is basically where we are calling this function. So we are loading these images and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here, and the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available and it will be shown in the other video, and frame by frame we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video, just look out for that. And actually the information about that is provided in the cards, the eye symbol. So that's the video object detection in video. That's the separate tutorial. All right, so now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here, these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there's something in the sky, and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images. In this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries, for example, NumPy, we need image IO, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. Alright, and then these are some warnings, we can just ignore them. So if I run this code once again, it will go away. Alright, and then here onwards we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line, is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells, we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build a model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. Things like that. So this mapping is done in this next cell. Alright, so let's keep moving, and then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images, so we are actually going to reuse, because video is nothing but it consists of frames which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is, here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code what we are doing basically is there are a few lines of code. What they do is basically once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image IO, so we can read and write videos using that. And the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like car. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is, once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video, we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that. But let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic underscore annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video underscore writer dot close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. I'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic underscore annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah. So this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our application will, our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video reader, video underscore reader, has a neat little feature or interface whereby you can say for frame in video underscore reader. So it will basically provide frame by frame. So you're in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is the cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here. It is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it.
In this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks we end up spending a lot of time in preparing the data for training, and with MNIST database we can avoid that. You already have the data in the right format which can be directly used for training, and MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation, and all of them are labeled. So you have the images and their label, and these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database, and the way we are going to implement this in our TensorFlow is we will feed this data, especially the